Hi, good morning, everyone.
Morning, doctor.
Hi, everyone. Good morning. I hope everyone is doing fine. So for today's lecture, I'm going to repeat Edu4, the first part of Edu4. Can you hear me clearly now? Hi, I'm doing sound check. Can you hear me?
Yes, doctor.
Yes, doctor.
Thank you. Because just now I was experiencing some problem with my microphone. Alright. Okay, nice. So today I'm going to repeat LU4 for the first part. I have recorded the second part and you can watch it later after we have finished this lecture today. Okay? Right. In learning unit 4, we are going to learn about acid and base. What are the definition of acid and base and the equilibria. We're going to learn about Ka, which is the acid equilibrium constant, Kb, base equilibrium constant. We are going to learn about I stable. I think everyone is already familiar about I stable when you are doing your foundation or SPPN. I stable is I for initial concentration, C is for change in concentration, and E for equilibrium concentration. But that one is going to be in the second part of the lecture. So the first part of the lecture, we're going to learn the basic definition on acid and base and some of the properties of There are many definitions for acid and base. Okay. We have Lewis definition, we have Arrhenius definition, we have Bronsted-Lowry definition. And in learning unit 4, I'm going to cover two definitions for acid and bases. First, the Arrhenius definition, and the second one is the Bronsted-Lowry definition. Okay. Right. According to Arrhenius definition, acid is something that increases H plus concentration in a solution, while base is something that can increase the hydroxide ion concentration in a solution. Example of acid is hydrochloric acid, and example of base is sodium hydroxide. I believe that you have encountered many situations when you need to use HCl as an acid and NaOH as a base. Basically, according to Arrhenius acid and base definition, every time acid and base react, they result in the product of salt and water. For example, if you have the reaction between hydrochloric acid and sodium hydroxide, it will result in the product of sodium chloride and also water. The sodium chloride here is the salt, here is water, H2O. This is the acid just now, HCl, NaOH is the base. Okay. According to Arrhenius acid and base theory, the definition of this, which is acid is any substance that can increase the H plus concentration in solution, and base is any substance that can increase hydroxide ion concentration in solution. So this definition confines to the aqueous solution setting. Okay, so you have the acid and base in the form of solution. So this is the definition that we use. Okay, let's take a look at another definition for acid and base. Excuse me. Okay. I have problems with this. May I just stop sharing first, and then I'm going to reshare now. Sorry for the glitch. Okay. According to Bronsted-Lowry definition, H plus ion is simply a proton with no electron. Okay? So this is a different definition of acid and base compared to the Arrhenius definition just now. Okay? So according to Bronsted-Lowry definition, the H plus ion is simply a proton with no electrons. So in water, the H plus in the aqueous solution they form clusters. So the simplest cluster of H plus ion is the hydronium ion, H3 of that. Okay, and H plus ion can also be in larger clusters, for example H5O2 and also H9O4 plus. Okay. But however, we generally use the H plus ion and hydronium ion, those two terms, to be used interchangeably during our discussion on acid and base equilibria. Of course, sometimes we can have these larger clusters of H5O2 plus and H9O or plus, but most of the time we are going to use the hydronium ion. Okay, it's the cluster of H plus ion. According to Bronsted-Lowry proton transfer reaction theory as well, acid donates H plus, okay, acid donates H plus, and base accepts H plus. Remember just now, acid is a substance with H plus ions with no electrons, okay, according to Bronsted-Lowry definition. So acid will donate H plus and base will accept H plus. A Bronsted-Lowry base does not need to contain hydroxide ion. So if we consider dissociation of hydrochloric acid in water, okay, hydrochloric acid solution, it will dissociate into H3O plus, which is the hydronium ion, and the conjugate base, which is the chloride ion. I will explain to you later what is conjugate base, but this is normally how we write the dissociation equation or reaction for Bronsted-Lowry acid and base. Okay? So according to Bronsted-Lowry as well, water can be had as either an acid or a base. So if you consider a beaker of water, H2O, there would be many molecules of water. Okay? Many water molecules. So these water molecules, they can be had as an acid, and also they can be had as a base. Okay? This is what we call as amphoteric substances. Amphoteric substances, they can be had as acids and as well as bases. Okay? Now, if we look at more on the auto-ionization of water, this is due to the properties of water, which is an amphoteric substance. So amphoteric substance, it can be had as acid and also as base. So in pure water, we have the following equilibrium. We have water, here, molecules of water, molecule 1, molecule 2, let's consider these two. They can dissociate into hydronium ion and also hydroxide ion. And this process is reversible. Okay? The hydronium ion and the hydroxide ion, they can turn into water molecules. And the water molecules can revert back to the hydronium and also hydroxide ion. So this process is reversible and they are constantly happening in water. Okay. When we talk about water as well, we can discuss about the equilibrium constant for water. Whenever we talk about any equilibrium constant, we should consider the dissociation reaction. Okay. Whenever we talk about equilibrium constant, we should consider the dissociation reaction. So this is what we call dissociation reaction. It shows how your acid or your base dissociates into hydronium ion or hydroxide ion and their conjugate. Okay, so talking about equilibrium constant for water, it can be calculated by multiplying the hydronium ion with the hydroxide ion concentration and divided by the concentration of the acid or base at equilibrium. Okay, so in this case, you have two, you have acid and you have base from both water molecules. So when you rearrange the equation, you have K EQ, which is the equilibrium constant, times the H2O square, the concentration of water square, equal to the concentration of hydronium ion times the concentration of hydroxide ion. So from here, you can rearrange as well. KW, which is water constant, equal to concentration of hydronium ion times the concentration of hydroxide ion. So add 25 degrees Celsius, this is the value for water constant. It is always like this. 1 times 10 to the power negative 14. Okay? So you remember the water constant is Kw equal to 1 times 10 to the power negative 14. Okay? Jot down in your notebook. Okay, let's go back to the previous slide. I was explaining about the water ionization, auto-ionization of water just now. It's because we were talking about the amphoteric properties of water. Okay. Right now, let's talk about the conjugate pairs. Whenever we talk about any acid or any base, they always come with a conjugate pair. Okay? So all acids, they will have conjugate base. And all base will have conjugate acid. Okay? So it doesn't matter whether you have a weak or strong acid or a weak or strong base, they always have conjugate pair. Yeah, remember, acid will pair with conjugate base and base will pair with conjugate acid. So within the Bronsted-Lowry theory, a conjugate acid is a species formed by the reception of a proton. So if you look back at the definition of Bronsted-Lowry theory just now, is that acid will donate H plus and base will accept H plus. Okay? Or a conjugate acid is a species formed by the reception of a proton. So a conjugate base is formed by the removal of proton from an acid, and a conjugate acid is formed by the donation of proton by an acid to a base. Okay. Right. So the conjugate base or conjugate acid is merely what is left after any acid has lost a proton or a base has gained a proton respectively. Okay, because we know that just now, according to Bronsted-Lowry definition, acid donates proton and base receive proton. Okay. So if we look at this table, at the top of this table, you can see a list of strong acids. These are some of the very strongest acids: HCl, H2SO4, sulfuric acid, NHNO3, nitric acid. All strong acids, they are 100% ionized in water. Okay? All the strong acids, the stronger the acid, the weaker the conjugate base. Okay? The stronger the acid, the weaker the conjugate base. However, the weaker the acid, the stronger the conjugate base. So this is also applicable to base. The stronger the base, the weaker the conjugate acid. And the weaker the base, the stronger the conjugate acid. Okay? So if you look at here, we have the strongest acid here. This is in this table, it indicates that the strength of the conjugate base is negligible. Meaning to say that it is tally with the statement just now. The higher the strength of the acid, the lower the strength of the conjugate base. Okay. However, if you look at here, this is weaker acid. The weaker the acid, the higher the conjugate base. Okay. The higher strength the conjugate base, okay, the stronger. So it is the same. So So if you look at the strength here, relative strength of acid and base, the stronger the acid, the weaker the contact base. Okay? So H plus is the strongest acid that can exist in equilibrium in aqueous solution, and hydroxide ion or OH negative is the strongest base that can exist in equilibrium in aqueous solution. So H plus here could be contributed by HCl, HNO3, okay, H2SO4, and so forth. And OH can become from the calcium hydroxide, sodium hydroxide, potassium hydroxide, and so on. Okay. Okay. We have learned the definition of acid and base, and also we also have learned what is conjugate acid, what is conjugate base. And then now we are going to move on to pH scale. Okay, so pH is a function, whatever we call P here is a P function is equal to negative log anything. Okay. Alright, so when we talk about pH, it's negative log H plus ion. And because we use hydronium ion interchangeably with H plus ion, it is the same. Okay, whenever we talk about negative log H plus ion, we can also, use negative log hydronium ion. Excuse me. Hello, tengah kelas. Okay. And then whenever we have POH, it means we have negative log of concentration of hydroxide ion. Okay. So in neutral water, we always have pH equal to POH equal to 7. Okay. And in acidic solution, H plus concentration is always more than 1 times 10 to the power of 97. So pH is less than 7 in acidic solution. So in basic solution, the pH is always more than 7. Okay. Alright. Most pH and pOH values fall between 0 and 14. So because pH plus pOH is equal to 14. So whenever you want to calculate pOH, it's 14 minus pH. And whenever you want to calculate pH, it's 14 minus pOH. Okay? The higher the pH, the lower the pOH, the more basic the solution. This is one example. Okay? The lower the pH, the higher the pOH, so the more acidic the solution. Normally, we always talk about pH, but for pOH, it is something opposite to pH. Okay? While there are no theoretical limits on the values of pH or pOH, normally for for determination of pH not using pH meter, we will always have a situation where the pH is between 0 and 14. However, if we check it by using pH meter, there is no theoretical limits on the value of pH or pOH which can be detected. For example, if we're dealing with pH of 2 molar HCl, okay, if you look at here, pH for 2 molar, again, we go back to the definition of pH. It is negative log concentration of hydroxide, concentration of H plus ion. Okay, so in this case, the concentration of H plus ion is 2 molar. Okay, so you're going to have the answer which is negative 0.301. In normal cases, we don't know if we have this kind of pH, negative pH, but if we use pH meter, we can detect the negative pH. later on we'll talk about pH meter. Okay? So for example, pKW is negative log Kw. Remember just now P function is equal to negative log. So if we have pKW, pKW means negative log Kw. Okay, we know that from our previous discussion, Kw is equal to 1 times 10 to the power negative 14 at room temperature. So this is a definite value. You should be able to memorize it. Okay, so pKW here is negative log concentration of H plus ion and hydroxide ion. Okay, and after that you can rearrange the equation, and you know that pH plus pOH equal to 14. Okay, what happened to my pen? Okay, let me unshare first. Okay, example 1. Calculate the concentration of hydroxide ion in 0.1 molar of HCl. So, although we have HCl here, excuse me, sorry, I still have problem with my pen. Okay, now my pen is okay. Okay, so calculate the concentration of hydroxide ion is 0.1 molar of HCl. How do we calculate hydroxide ion in an acid? Remember just now we mentioned that in all acids they have conjugate pair, which is the conjugate base, and in all base they have conjugate acid. Okay, so at some point in any solution, in any acid or base solution, we can have the concentration of both hydroxide ion and the concentration of H plus ion. Okay, now how to solve this problem? Go to the equation Kw equals to concentration of H plus ion times concentration of hydroxide ion. So you know that Kw is 1 times 10 to the power negative 14. This is a fixed value. And you know from the question that the concentration of H plus ion is 0.1 molar. Okay? So you have 0.1 molar put into the equation here, but you are going to find what is the value for hydroxide ion. So after you calculate, you will get the answer for concentration of hydroxide ion. Okay. Although the self-ionization of water is ignored in calculating H+, the self-ionization equilibrium still exists and is responsible for a small concentration of hydroxide ion. So this is the explanation why you have conjugate pair. Because the acid is in a solution form, so although you have H plus contributed by the acid itself, but you can also have a small amount of hydroxide ion contributed by the auto-ionization of water, which is the solvent for the acid. Okay. Next question. Calculating the concentration of H plus and hydroxide ion in solution of a strong or base. Strong acid or base. So calculate the concentration of H plus ion and hydroxide ion in 0.15 molar of nitric acid and 0.01 molar of calcium hydroxide. So first, before we continue to answer or solve the problem, the first thing that you need to do is always to write the balance dissociation reaction. So in this case, in the first case, you have nitric acid. Nitric acid dissociates into H plus ion and the conjugate base, which is nitrate. So H plus ion given in the question is 0.15 molar. Why? When we talk about molarity of any acid, it is contributed by the H plus ion. So if we have HNO3 here, 1H, so the concentration is 0.15. However, if we are dealing with H2SO4, when we talk about 0.15 molar of H2SO4, it is normally 2 times the concentration of H plus ion is 2 times 0.15, okay, which is 0.3, is it? Okay. So in this case, we have nitric acid. So the concentration of nitric acid is 0.15 molar. So this is also the concentration of the hydroxide ion. So you're done calculating the H plus ion concentration in nitric acid. So now you need to calculate the hydroxide ion concentration. So how do you calculate the hydroxide ion concentration? It is based on the equation just now. Kw is equal to concentration of H plus ion times concentration of hydroxide ion. Okay, you know the value here is 0.15. So Kw is 1 times 10 to the power negative 14. So you can find how much is the hydroxide ion. Okay. Now move on to the next example, which is for calcium hydroxide 0.01 molar. The first thing that you have to do whenever you want to answer any acid or base equilibria problems is that you have to write the balance dissociation reaction. So CaOH2 is a strong base, dissociates into Ca2 plus and also hydroxide ion. So when you balance the equation, you have Ca 1, 1. You have 2 OH over here, so you have to put 2 in front of OH on the product side so that you have a balanced equation. So from there, you know that any concentration given in the question for calcium hydroxide must be multiplied by 2 because you know that you have 2 coefficients for the hydroxide ion. So 2 times the concentration given in the question, 0.01 molar. So you get the concentration of the hydroxide ion. Okay. So you get the concentration of the hydroxide ion, which is 0.02 molar. So how do you find the concentration of H plus ion? Again, we utilize Kw equals to concentration of H plus ion times concentration of hydroxide ion. So concentration of H plus ion is equal to Kw divided by concentration of hydroxide ion. Okay, so Kw is 1 times 10 to the power negative 14 and OH is 0.02 molar. So from here, you know what is the concentration of the H plus ion. Okay. Alright. And another question is for you to find the, there's no question. Right. So here there is one extra question, extra answer here. It's calculating the pH. pH is easy. pH is negative log H plus ion for any acid. And for a base, if you already have the concentration of the base, you can calculate the pOH. pOH is negative log the concentration, negative log concentration of hydroxide ion. And then from there, you can use pOH plus pH equal to 14, and then from there we can get the final pH. Okay, but the most important thing here is that the question is asking you what is the calculation, what is the concentration of the hydrogen ion and hydroxide ion in both of the acid and base the questions. So we know that for any acid you can also have both the hydroxide and hydrogen ion at the same time, and for any base that is also the same case. Okay. Now example 3, a solution of barium hydroxide is 0.125 molar. What are the concentrations of hydrogen ion and hydroxide ion in the solution? Again, the first approach is for you to write a valence dissociation reaction. You have barium hydroxide dissociates into Ba2 plus and OH. So if you look at here, you have one Ba and at each side of the reactants and the product, but you have two OH in the reactant side, so you have to add two coefficient in front of the OH on the product side. So in this question, the concentration of barium hydroxide given is 0.125 molar. So the concentration of barium hydroxide is not necessarily the same with the concentration of the hydroxide ion, because if you want to calculate the real concentration of hydroxide ion, you have to multiply by 2, which is the coefficient in front of the hydroxide ion. Okay? So 2 times 0.125 molar becomes 0.25 molar. So this is the concentration of the hydroxide ion. So how do you find H plus ion? You use Kw equals to the concentration of H plus ion times the concentration of hydroxide ion. From there, you can find what is H plus ion. Okay, so you get the answer. I don't know, is it this one or this one? Let me calculate. So this is not the right answer. This is 4. Should be 4. Okay. 4 times 10 to the power negative 14. This is the correct answer. Okay. Now we move on to how we measure pH. Normally we on our secondary school we always measure pH by using pH meter. Using a pH paper, but the most accurate method to measure pH is actually by using pH meter. Because by using pH meter, as I have mentioned just now, we can detect even the negative pH for the solution. Okay? Alright. For a quick indication of pH change during any titration, however, we can use indicator. Okay? What is indicator? Indicator is a substance derived from a weak acid or a weak base which can change color once the pH change happens. Okay? So these are dyes. They are dyes that change color when pH change. So these are called indicators. Although indicators are less precise compared to pH meter, it can give you a very quick and simple indication of the endpoint of your titration, acid and base titration. Okay. Alright. So this is just a revision. Okay. Yeah, this is just a revision. pH is equal to negative log hydronium ion or negative log H plus ion. POH is equal to negative log hydroxide ion, and negative log hydroxide ion. Always remember. Always also remember Kw is equal to concentration of hydronium ion times concentration of hydroxide ion equal to 1 times 10 to the power negative 14, and pKW is always pH plus pH. It always equal to pH plus pH and always equal to 14. Okay, so you know that pKW is 14 and pH plus pOH is also 14. Okay, so these values, they come from the KEQ for water, water constant. So this is the pH scale. This diagram is showing you the pH range for color change for several types of indicator. So if you look at the table here, different indicator has different range of pH which they change color. So they can only be used for titration that has an endpoint or an equivalent point at that particular pH range. For example, in order for you to use methyl violet, it is only applicable if you have a titration which has endpoint or equivalent point occurring between 0 to 1.5 only. Okay? However, some indicators, they can also act as indicators in both acidic and basic condition. For example, cyanide blue, it can change from red to yellow between pH 1 to pH 2.5, and it can change from yellow to blue from pH 8 to pH 9.5. So this is example of how we use indicator. Okay, we use it for the describe pH range. Okay, so let's say you have a titration between acid and base, which the endpoint or the equivalence point is expected to be at pH 5. Okay, so what are the examples of indicator that you can use? The best type of indicator that you can use is an indicator which shows the pH change after pH 5. Meaning to say that although you see here methyl red can change color at 4.5, pH 4.5, it cannot be used as a suitable indicator for your titration just now, because your titration, the equivalence point is pH 5, because it changed color earlier than pH 5. Okay? However, if you have an indicator which turns change color at pH 5.1 or 5.2, you can use it as an indicator. Okay? I think this is the last slide for today. The last two slides for today, the properties of acid and bases. Okay, these are the common list of strong acid. Strong acid, normally they have H plus concentration at high level, and they fully dissociate. Okay, so they have 100%, 100% dissociation percentage. Okay. So the strongest common acids are as listed here. We have things from hydrochloric acid, hydrochloric acid, and then HNO3, and then H2SO4. We have this 7 1, 2, 3, 4, 5, 6, 7. So we have 7 strong acids, which is common. Okay, these are not the only strong acids, but these are 7 common strong acids. Okay. Strong acids are strong electrolytes, okay, because they have high content of H plus ion, and all strong acids ionize completely in solution. As I mentioned just now, all strong acids have 100% dissociation. It's different from a weak acid. Weak acid has less than than 100% dissociation. That's why it's called weak acid. But for strong acid, it ionizes completely in a solution. For example, nitric acid dissociates into hydrogen ion and also nitrate. Normally for a strong acid, in any solution of strong acid, the strong acid is usually the only source of H plus ion. Okay, we know that in any acid solution, the solvent is water. So they are somehow in this solution auto-ionization process of water. Remember just now auto-ionization of water? So you remember as well that auto-ionization of water in an acidic solution contributes to the OH ion, the hydroxide ion in an acid. Okay, and as well as auto-ionization also contribute H plus ion apart from hydroxide ion. This is because water is an amphoterically substance and it can behave as acid and as base. Okay, so this is a revision. However, in a strong acid, normally the only source of H plus is from the acid itself. Although we have this acid in water, okay, the H plus contributed by water in the strong acid solution is normally negligible. Okay? Why? Because they are very small amount, very small concentration. Okay. So if the molarity of acid is more than 10 to the power of negative 6 molar, then you should assume that the only source of H plus ion comes from the strong acid. However, if the molarity of acid is less than that, is less than 10 to the power of 6 molar, then the effect of auto-ionization of water must be considered. Okay. What about strong base? The most ionic hydroxides are strong bases. For example, sodium hydroxide, potassium hydroxide, calcium hydroxide. Okay. Strong bases are strong electrolytes and they dissociate completely in solution. And the pOH, and hence the pH of a strong base is given by the initial molarity of the base. Okay. So you have to be careful of this stoichiometry. What it means here is that if you have 1 molar of KOH, if you have 1 molar of KOH, if you write the dissociation constant, KOH dissociates into K plus and hydroxide ion. So you have 1K and 1K on both sides, 1 OH and 1 OH on both sides. So 1 molar of KOH is normally 1 molar of hydroxide ion. However, if you have calcium hydroxide, dissociates into Ca2 plus and hydroxide ion. So you have to balance the equation, the dissociation equation. So both sides should have 2 OH. So if it's a 2 OH, if it has 2 OH, then both the, you know that the concentration of 1 molar CaOH2 is the same, is not the same with the concentration of hydroxide ion. Concentration of hydroxide ion should be 2 times 1 molar. Okay, which is 2 molar. So that's why it's mentioned in the note here, be careful of the stoichiometry. So what we have learned in this lecture are 3 things. Okay, there are 3 things that we have learned today. The first thing is the theories or definition of acid and base, which is based on Borstet-Lowry theory and also Arrhenius theory. The second thing that we learned today is about the KW. We know that we know the relationship between Kw and as well as pH, pOH. Okay. We know also that in order to in order to find uh, the pH, you have to calculate by using negative log the concentration of um, H plus ion, and in order to find the pOH, you have to calculate by using negative log concentration of hydroxide ion. Okay. We also learned that the third thing, we also learned that in any acid or base, they have conjugate pair. So these are the three things that is the basic knowledge that you need to know when you're considering any problems related to acid-base equilibria and acid-base titration. Okay, so I think that's about it for our lecture today. I will upload the recording on eLib. The recording for the second part of LU4 is already available on eLib, and I hope you can use the time allocated today to watch the video. Okay, and try all the examples. Okay, don't just listen, because if you listen only, you can retain the information only for a short period of time, but if you do it, you can understand more and the memory will last longer. Okay, all right, thank you very much everyone for having me today, and I hope if you have any questions, you can post it in the WhatsApp group for everyone to study as well, and I take note of your manual attendance. Okay, oh, I have some question here from you. Doctor, does it mean that there are no difference if we use either negative log hydronium ion and negative log H plus ion? Yes, no Shahada, it doesn't matter whether you use either one, because it will result in pH as well, the same thing. Okay. And Monica asks, I am quite confused about equilibrium constant and water constant. Okay. Okay, equilibrium constant, they are equilibrium constant for acid, they are equilibrium constant for base, and for water, we have water equilibrium constant. Okay, so for water equilibrium constant, okay, let me just go back to the slide just now. This slide just now. Water, KW. Yeah, okay. All solution, they have KEQ. Okay, all chemical solution, they have the equilibrium constant. Kw is the equilibrium constant for water. Okay, so this is the normal way to calculate any KEQ or any equilibrium constant. Normally we have the product side here times with the other one. In this case, for water ionization, you have to consider two molecules of water dissociates into H plus ion or hydronium ion and also hydroxide ion. Okay, so from there, you put it into the equation. This one will be explained more in the second part of the lecture. Please check it out. Okay, so KEQ is equal to the concentration of the hydronium ion times the concentration of the hydroxide ion divided by the concentration of the water. Because water here, they do have S, the acid and base, both acid and base. So concentration of water square. Okay, so from here we calculate it, and the value for Kw is always 1 times 10 to the power negative 14, which you need to remember in all calculation involving acid-base equilibria. Kw at standard room temperature is 1 times 10 to the power negative 14. Okay, I hope that will answer your question. I still do not I still do not understand about auto-ionization of water, about the molarity part. Isn't it easy in example 1 or 2, the concentration is more than 10 times. Example 102, the concentration is more than 10 times -6. Example 1, I'm not quite sure what do you mean by that, but let's see example 1. Oh, okay. Example 1 and example 2 is simply showing that in all acid, somehow there would be an amount of hydroxide ion concentration in all base, somehow there will be some amount of H plus ion concentration. It's just that whether they are negligible or not. That's all. Okay. For example, for strong acid, of course, we have a negligible amount of hydroxide ion, and for a strong base, of course, we have a negligible amount of H plus ion. The point here is that because all the acid and base, they are in a solution form, there is somehow an amount of OH plus or OH negative or H plus ion is, is contributed by water, okay, to the acid or base. Although they are at a very small concentration and negligible. Okay, but the point is it's there, but sometimes you don't consider it as part of the calculation because it is in a very small amount. All right, I hope that answer your question. All right, thank you so much, everyone. Thank you so much, everyone, and I'll see you next week, inshallah.
Thank you, Doctor.
Thank you, Doctor.